welcome everybody. I'm really looking forward to talk to you. I will talk roughly 45 minutes, and afterwards we have 45 minutes to discuss everything you want to know. I'm really happy for any questions that come up and any kind of things you want to know. My topic is anticipating the future response of high mountain permafrost to climate change. And I think that fits very nicely into the context. I will show a lot of examples from the Alps, but basically the physics and the geomorphology and the destabilization underlying these processes is quite the same that you will observe in the Himalayas. This often requires a long-term study series, which we have in the Alps, and I would be very happy to see more of those also in the Himalayas. This is a lot of process understanding we have to develop, and I think that's quite important because, like for many of the other hazards we have a kind of a generation-long history of knowing how things happen. But what will come in the next 50 years in the Alps, like your grandfather can't tell you that because he's never seen that. So we are running into a real new experience of alpine hazards, and that is unprecedented. So we can't go to the past to really see what happens. The only thing we can do is scientists can develop an understanding of what will happen, and this we can then use, and this is also a challenge for communication, I think. Okay, with this, I'm taking you to the Ötztal in the Austrian Alps, and you see UltraCam records from 2009 until 2018, and these have a ground resolution of 20 centimeters. So we, in a project we're having at the moment, we reanalyze the entire data set. You see the height loss of glaciers is 25 meters. This is in the reddish colors. At the same time, we also develop new lakes, and having frozen rock faces nearby lakes always generate a certain security issue because you can generate flood waves into that. So what you can see is first the retreat of these glaciers is quite remarkable. At the same time, we're generating like new features like lakes. But we should not only concentrate on the glaciers because there's a lot of hidden ice in the slopes surrounding the glacier. And this is something you just see. You see it's not only the glacier like retreating, but it's also like the slopes around start to move. So my talk will be a lot to not only talk about the visible glaciations, the visible ice, which are the glaciers, but also talk about the invisible things, which is the lot of ice that we have in debris and in rock faces, because this is undergoing a change over the next 100 years. It will stay longer than the glaciers, and it has significant impacts on the stability we have. So if you look at this from a geomorphological point of view, we'll see this as a rock glacier, but you also see we have accelerating and significant movement in the ice and debris here, movement rates of meters per year now, and these cause significant issues for engineering problems. Okay, let's start with the highest mountain of Germany. This is the Zugspitze, and this is the highest spot of it. Some call it the highest beer garden of Germany, 2,960 meters up above there. If you look at it from a geo point of view, you will also see that this big feature here. And basically, this is a part of the Zugspitze that is now missing. So it used to be a peak 3,050 meters high, so a little bit higher than today. And this was 4,000 years ago. And 4,000 years ago, the Zugspitze detached in big two rock slope failures and created a massive energy amount. So upon the impact of this rock mass in the Eibsee basin, it emitted probably in 40 seconds, something like 50 Hiroshima bombs of energy that mostly went into the fragmentation of its mass. It created a really fast rock avalanche that was 200 kilometers fast and went across the Garmisch Valley and up on the opposite side, 200 meters high, and then turned to the now city of Garmisch-Partenkirchen. So if we look at this, some people said like this big rock slope failure at the Zugspitze is connected to the degradation of permafrost. And in this lecture today, I try to bring you to a point where you can decide on your own whether you believe this, where you think, is it possible that really permafrost degradation in a mountain like this could cause such a big rock slope failure like the Zugspitze? So this is the basic question we try to answer today. And for this, I'm going to take you to some examples. So present day, we only have permafrost in the upper part of the Zugspitze. The line I show you here is roughly 2,800 meters. And above on the north facing, we still have permafrost. But there's also older permafrost in the core of the Zugspitze, which is a memory effect of former times that were cooler. So we're trying to that. If we try to bring that into a modern perspective, the closest analog I can think of is the Yigong rock avalanche in April 2000. So if I draw you a line here, this is roughly 5,000 meters. So we have a detachment that is very high. It's at the fringe of Tibet, of the Tibetan plateau. This is a volume that is very similar to the Zugspitze detachment, and we just quickly go through it to see how it does. You see like the rock mass rapidly fragments into smaller particles, and in this case a volume similar to the one of the Zugspitze detached, and it caused the blocking of this river here. So this 6,200 meter high landslide dam blocked the Yigong Tangbo River. The instantaneously starting flooding above affected 4,000 people. Several schools and villages had to be closed, and also Yigong Tea Garden. China put a lot of force and efforts into it and create an impressive channel. It was 1,000 meters long, 150 meters wide, and they excavated 1.4 million cubic meter. But in spite of their very busy activity, they realized in June 3 they are not going to make it. And a catastrophic breach of this started at June 10. We can estimate the maximum discharge from this in June 11, and this is a very impressive number, saying like 120,000 cubic meters per second discharge. And this is estimated at a bridge that is 17 kilometers downstream, and the water level was at least 34 meters above bridge decks. If you have this massive floodings, they become like hyper turbulent in a certain way, and the turbulent is so strong that they would even take steel parts and deform them in a significant way. So they cause massive destruction. And even in India, which was reached after 216 kilometers in China, 450 kilometer downstream, it still generated a 5 meter high flood wave. And in India, 20 bridges were destroyed and 50,000 people were rendered homeless in this. Okay, if we compare that to more recent other rock slope failures, we can ask why should we care about them and what is the basic hazards we have associated with them. And one of the very famous examples is this rock slope failure, 50 million cubic meter on a glacier. So an addition of 50 million cubic meter of ice eroded here and caused 140 casualties in a village down here. A more historic event in the 1970s, we can probably also connect to permafrost, is the Huascaran. Certainly there was earthquake shaking above, but the destabilization occurred in this permafrost flank above here, and it caused a big rock ice avalanche with 50 to 100 million cubic meter and caused 20,000 people dead in these two villages. This is the things we are pretty much aware because they are reported in media. Bigger problems in the Alps, I think, are less spectacular and less reported. They are the widespread subsidence that causes problems for infrastructure. We have at least 30 alpine cable cars that have significant problems with subsidence, and I'm talking about values of 50 centimeters per year or something. And as a cable car, you shouldn't have more than millimeters per year. What you see here is the cable car at the Gems stock, and this is a deformation of 12 centimeters that occurred within one summer. So these cable cars, they spend incredible amounts of money to stabilize their stations, and the kind of solutions they develop are very costly things. So some of them use active cooling in the cellar to cool from the bottom plate. In Andermatt, they use artificial textile coverage of the rocks, which costs something like 500 euros per square meter to install every summer, and they really have to install a lot of this. Other stations like the hut in Ischgl, which is very important for the local ski industry, has like a hydraulic base that can take up deformations up to 40 centimeters. So with all kinds of very costly investments in these kind of cable cars to compensate for these effects. Okay, if we want to understand the thermal dimension of permafrost, and we look at the mountain permafrost, we see is only a small part covered with that. So if we take the northern hemisphere map of permafrost, we see we have a lot of Arctic permafrost. And besides, we only have certain regions like the Rocky Mountains or the Himalayas or the Alps or the Scandis, where we have what we call alpine permafrost. So the importance of alpine permafrost is not the big methane emission or carbon dioxide emission problem we have because of the big size of the 25% northern hemisphere covered by permafrost. But the alpine permafrost, the problem is more that it's much more densely populated, it's intensely used by tourists. And there's quite a lot of pressure in recent decades to go into that, because all ski resorts that really make money in the Alps are very high up and have a long snow season. So the ski resorts actively move into the most endangered parts in terms of permafrost. If you look at such a rock surface, you might understand why it's not so easy to calculate the amount of permafrost in a rock slope. You see, like, snow accumulates on patches. Even on that 2 by 2 square meters, you have very different aspects of the rock face. You see, snow can even stick to rock faces in very steep conditions. You have fracturing where water can percolate into rocks. So you see, there's all kind of variability. So if we want to come up with a picture like how permafrost evolves over the next 50 or 100 years, we have to take into account not only temperature changes, but also changes in snow covers and others. I'll be more specific in a minute about this. I think this is in the background of climate change in mountains, and I deliberately took 2055 because that's in your lifetime, and that's much nearer. You see the expected warming in the European Alps, for example, in a global environmental scenario would be in the range of 2 to 3 degrees until 2055. In a global economic scenario, you would rather expect something like 3 to 4 degrees in there. From this, you can generate very generic maps of permafrost distribution. Here's, for example, the permafrost distribution in Switzerland. And you see that major touristic centers like the Matter Valley and Zermatt and St. Moritz and Grindelwald are right in this range where we have permafrost occurrences. Let's quickly go through the thermal properties of alpine permafrost. Glaciers are not always warm. We have these warm glaciers down here, which have, due to their height at the base, temperatures of 0 degrees and water. Under these glaciers, we don't have permafrost because they're simply warm-based glaciers. In higher altitudes, so in the Alps above 3,400 meters, and a lot also in the Himalayas, we have cold glaciers, and these cold glaciers are directly frozen onto the grayish thing here is permafrost, onto permafrost. So, and they provide a very effective thermal conduction. Some of the problems we see in the recent decades, I think, is the change of these cold glaciers to warm-based glacier, and this rock below then sees for the first time in a long history plus temperatures, so above 0 degrees. And I think this is quite a hazard. If you then consider an active layer, which is the orange indication, let this be 3,500 meters in the Alps. So if you go down, the thickness of the active layer, which is the part above permafrost, which thaws one time in a year, becomes thicker. If you go to a mountain like the Zugspitze, which is inside, always frozen at a temperature of -1 degree, you get something like 4 or 5 meters on average per summer that constitute an active layer. If you have a very warm year like 2018, this active layer can increase up to 10 meters. These are summers that generate a lot of rock slope failure. I go quickly over that. So we have different heat fluxes. There's short wave radiation, we have long wave radiation, and these have quite important amounts. You see, it's 100 watt per square meter in summer, so they are the most important intake and outgoing energy flux we have in there. The next energy flux we have on these rock faces are sensible and latent heat fluxes. So sensible are those you can measure in temperature. So cold air will act to decrease the temperature. And latent heat fluxes are those if you, for example, get snow coverage or ice coverage on the rock surface, it will also have an effect. Because like when you get the first snow on a warm rock face, it will start to melt the snow. And this is quite an important energy flux. And then we have geothermal and transient heat fluxes. Transient heat fluxes are those that come from the past. So many rocks are inside colder than they would be under present day equilibrium conditions. If you take the Matterhorn, there's a good physical modeling of that. The Matterhorn inside is still 2 degrees colder than it would be under present day equilibrium conditions. And this is because it still hasn't warmed up since the last glacial maximum 20,000 years ago. So we still have to consider that inside bigger mountains, we have a core that is much colder than we would expect under present day conditions. And so then the basic process we have inside the rocks is then slow heat conduction, and this is buffered by the latent heat of ice inside the pores and fractures. And we also have to consider that we have fractures in there, along which we have an anisotropic behavior of heat transported along water, air, and ice-filled fractures, which is a difficult topic. Okay, let's summarize this in a permafrost model of the Zugspitze, like what is in there. So for this model, you see like this is the Zugspitze. You see the black line is 0 degree. We have permafrost on the north face in a range of 0 to -2 degrees. On this side, the south face is free of permafrost. So what do you need to put in a model to create a model like this is basically long and short wave radiation, a sensible heat exchange along the rock surface, and internally you need heat conduction. You consider thermal conductivity of the rock, you consider certain heat capacity, and you very importantly have to consider a water-filled porosity, because that water you have to change from frozen to unfrozen. This implies that we have a number of shortcomings of things that are not in the model present day. This is, for example, the snow and ice cover, which is quite an important factor influencing the local distribution of permafrost. We don't include subscale topography like overhangs or like features that take away the sunlight, which makes a big change for the permafrost distribution. We don't consider petrophysical variability, and we don't consider the anisotropy of fractures or something in such models. Okay, with this introduction, we can now go to the effects of it and see, like, if we have permafrost in the Alps and the Himalayas, and it's started to warm 20 years ago, what are the effects that we can expect? And can the effect be so big like a Zugspitze rock slope failure? What's the maximum scale at which we can consider these instabilities? This is a paper from me from 2013 where we try to conceptualize the different influences that exist on warming permafrost rocks. So in any kind of slope instability, you have a certain fraction of the gravitational force. What is different now in permafrost? One of the things that is different is, for example, the hydrostatic pressure. Above ice, water starts to accumulate because it cannot run through the impermeable fracture. So ice makes fractures impermeable. We're measuring at the Zugspitze and we see we have 20, 30 meters of a water column above. And these water columns generate significant pressures that can act to destabilize mountains. Another important factor are cryostatic processes, and they are also referred to as ice segregation. I think this is quite a common experience for people living in colder countries like we do here, where we have winter. So then as a kid, you were told to not lick on a metal in winter. And what everybody expects is that your tongue instantaneously freezes to that metal, but it doesn't do that because the thermal inertia of your tongue is too big. So what basically happens if you lick to a sub-zero degree metal part outside is basically that at the time you put your tongue there, it creates a small ice film on that metal. And that ice film sucks the water on your tongue with a cryostatic pressure that is in the range of 2 megapascals. So at that time, you can't get your tongue off because that starts instantaneously. And then over the next 1-2 minutes, your tongue really starts to freeze to that metal part. So that's your personal experience with cryostatic pressures. But I think that's quite an, if you consider rock slope failures in the Alps, this can become quite an important factor, because along all the fractures that are ice filled, this ice starts to suck out the unfrozen water content from the surrounding rock. And by that, it starts to extend the size of these ice filled fractures. And this extension can be up to 1 centimeter or so over a winter. And if this fracture is extending, this is quite high pressures. So we've seen blocks with a size of 10 by 10 by 10 meters pushed out by 1 centimeter purely due to ice aggregation in the Swiss Alps over one winter. Of course, like ice does not only put additional shear forces on these rock blocks, but it also has like a supporting or a like stabilizing effect. And this is the other things we have to look at. So if you want to deform that block, if you want to deform ice, you have to put a certain shear resistance on the ice, and you will see in a minute that it's not difficult to deform ice if you have enough time. If I would have perfectly isolated gloves and an ice cube, while I was talking here, I could have deformed it quite a little bit. But if I try to make it fast, the ice puts a resistance to it. The other factor we have to talk about is the fracturing between rock and ice interfaces. We have to think about friction, and we have to see about the breaking of rock bridges, so which connect these things. Okay, if we try to put all that together, we can start to understand why permafrost rock slopes start to destabilize when they warm. The first important thing to understand is it's not only the ice and fractures, but it's the rock itself that starts to warm. So if you have a sandstone, this is a classical sandstone, Berea sandstone, and you take the compressive strength. So if you have a cube of that, and you just try to, what kind of strength can I put on it before it breaks? You will see at -8 degrees, you have 15 megapascal, at 0 degree, you have 4 megapascal. So it loses 75% of its, this is the tensile strength in this case. So if you pull it away, it loses 75% of its tensile strength when it thaws. And the same is true also for compressive strength. So you have a significant reduction here of the compressive strength, more in the range of 25 to 50% when it thaws. So the first thing we have to realize, the compressive and tensile strength of rock significantly changes when they start to thaw. The second mechanical factor we have to integrate into this is fracture toughness. So if I have a rock bridge like this and I try to deform it like this here, a limestone similar to that at the Zugspitze will lose 37% of its fracture toughness. Okay, and with that we can start to understand how these rock slope failures start to evolve. Visualize I'm the rock slope failure that wants to fall down. At my back I have 10 rock bridges. Okay, and then I start to warm, and suddenly all the 10 rock bridges at my back lose 37% of their fracture toughness. And then it's not unlikely, or it's quite likely, that one of these 10 rock bridges that keeps me in position, rock bridges are intact rock connections from me to the rock face behind, that one of these 10 can no longer take my load. Okay, so the shear stress I put on it is too big and it starts to fracture because it has undergone a reduction of 37 degrees of fracture toughness. So if I do that, I put my weight then on the other 9. And the other 9 have also just experienced this 37% loss in fracture toughness. So it's quite likely that the 9th rock bridge break, and then the load is too big for the other 8 and they start to break. And this is how rock slope failures start. And this is why we see this accelerating velocity in them. So rock mechanics are quite related to the initiation of rock slope failures in thawing permafrost rocks. Okay, this I do relatively quickly. If you want to deform ice, the shear stress you have to overcome to deform it is dependent on the rate of deformation. If you deform ice slow, you need basically no stress and no energy to do that. If you do it pretty quick, the ice puts a significant resistance to that. So at very low velocities at which, for example, cracking of rocks occur, the shear resistance of ice is negligible. And fracturing only happens if you have higher velocities. So that would be strain rates where you say several millimeter per hour or something like that. I have to say sorry now, because this has been the toughest part of the presentation today, and I'm very happy for those who managed to follow the last ones. I try to put it together now, because with this we have now a real framework of saying, like, why do rocks that start to thaw become unstable? Because previously, like, it's been just told that the ice is away and therefore rocks destabilize. If you look at this formula, which we have just developed in the last 5 minutes together in this talk here, you will see that the shear resistance of this failure depends on a number of factors, which is the fracture of rock bridges, the total friction, the deformation of ice itself, and rock-ice interfaces. And you can see that the yellow components respond to thawing or to warming permafrost temperatures. So if you warm the rock, you decrease the fracture toughness of these rock bridges by 37% for limestone. You decrease the friction because it depends on the uniaxial compressive strength. You increase the deformability of ice because it's directly dependent on temperature. And you also change the failure criterion of rock and ice because this also depends on temperature. So suddenly we can not only guess that rocks become more endangered when they become warmer, but we can put it in a mechanical context and really understand why it is. Okay, with this we can now do nice mental experiments, because we think, like, is something like the Zugspitze a real big rock slope failure? Is that possible in there? Okay, so let's start to do 2 mental experiments with that. The first is the destabilization in time. Okay, the first day of instability. I still have rock bridges at my back. And as long as I have rock bridges, I deform so slowly that I can't put a significant amount of the shear stress to the deformation of ice, because ice is not putting any resistance to slow deformations. So the first day of instability is purely rock mechanically defined. It's defined by fracture toughness of rock bridges, and it's defined by the changes in the friction. So this is the first day of rock instability. At low velocities, rock mechanical processes dominate initial destabilization. Only at a time when I've cracked all rock bridges, I can start to accelerate to something like millimeters per day or something. And then ice starts to put a certain resistance to this movement, because we're now getting a deformation rates that are important for ice. And only if we become more accelerated, we can come across the threshold we need to crack the rock-ice connection. So if we take this in time, we start with the rock mechanical processes. These are the first day instability, and only in the last week or something, where we have rapid deformation, ice puts really some resistance to it. Okay, let's think about how big those rock slope failures from permafrost rocks can become now. In previous papers, like, all people regarded ice segregation as the most important process. But if you look at ice segregations and you have depth of the shear plane with a rock overburden more than 10 meters, ice segregation does not work because it has a shut-off pressure and it's not important. This is also true for the other ice fracturing processes. If you have more than 20-meter rock overburden, these processes cannot operate because you can no longer build fractures, because the ice suppresses fracturing under higher pressures. So if we want to talk about the real big ones, the big rock slope failures that come down from permafrost, the only good argument we have mechanically are friction and the fracturing of rock bridges. So these are the only arguments we have to understand why big rock slope failures like the Zugspitze could be connected to a change in temperature. And because nobody published that before in the 2013 paper, we called it the presently unexplained space, because with this suddenly we can explain that large rock slope failures happen from that. Okay, that was the toughest part of the talk. Now you can relax. We're looking into examples, and we try to, if we can really reproduce the things we see here in the lab and in the field. For this, we go to a number of alpine sites, the Zugspitze, Kitzsteinhorn, which is also a nice cable car construction in Austria, close to Salzburg, and the Matter Valley, where I did my PhDs on this stuff. To find out how rocks mechanically change upon thawing, we use non-destructive techniques. So we look at what's the velocity of P-wave velocities in this sample and how does that change upon freezing. And we also like to use very destructive techniques. So this is a hydraulic instrument that can do 40 tons on a sample. And with this, we can crack unfrozen and frozen samples and compare how they perform under it. And the same we can do also in this way with tensile strength. And this is then called resilient test. Okay, if we do that, we have an issue because we don't use engineering materials, we use real materials. So if we want to find a difference between frozen and unfrozen stability or strength of Zugspitze limestone, we can't take 5 samples or 10 or something. We have to take something like 80 or 90. So that puts a lot of work on us. And you see how they break if they get into it. So we need statistic amounts of samples. We need to change the scale to see how important are fracture patterns. And rocks that have an anisotropic pattern, we have to change from different directions to see like if that applies to all directions. Let's quickly go over the changes like physically rocks do when they start to thaw. The first remarkable change, I go pretty quickly over that, is that the electrical resistivity of these changes quite a lot. So if that is the unfrozen resistivity, this is the electrical resistivity that changes gradually. Upon freezing, suddenly the electricity can't penetrate through the rock very well anymore because it uses the water in pores to penetrate through it. And if the water in pores starts to freeze, there's decreasingly ways and pathways for the electricity to the rock. So we can see a very strong increase in the resistivity upon freezing, which is not exactly at 0 degrees, but a little bit lower due to several effects on this freezing. Okay, I go quickly over this. And with this, we can make this kind of experiments here. And this we can later use then to do geophysics to see whether these rocks are frozen. You see, like for the Mutter Valley, so at 20,000, you're at -1. At -3, you're already at 40,000. So there's a quick change in the electrical resistivity that can help us to detect frozen proportions inside rock. The same is true for P-wave velocity. So here we kick a P-wave velocity, P-wave through the rock sample from Matterhorn, and we look what happens at the freezing point. You see, freezing point is -0.9 degree here. And upon freezing, you see that the P-wave velocity rapidly increases. And this is also mechanically quite interesting because the P-wave velocity is the best correlated factor of the fracture toughness. So we know between -5 and 0 degree, we have a massive change in the fracture toughness in these rocks. Okay, we've done this for quite a number of rocks, so 22 alpine and Arctic rock samples. And we see that not all rock types are similarly susceptible to these changes. You see quite a big change in carbonate rocks. So the P-wave velocity changes 75% upon freezing. Also schists, volcanic rocks, clastic rocks are quite sensitive. And we see some rock types like gneiss or so are least affected, but they still have like changes in the range of 7-8%. Okay. The second thing we have to care about is like it's not the same if a rock freezes one time or it freezes repeatedly. And for this we use fatigue. So we take rock samples. This is from the Three Gorges lake reservoir from the dam. This is the stabilizing elements are drilled into the sandstone. We took a lot of samples, we froze them, and we took, after every freezing, we took 2 out of them and tested how they mechanically perform to see how tired they get, how the fatigue proceeds. And you see over 18 freezing cycles, the compressive strength decreases by 30%, and the tensile strength decreases massively in 17 cycles. So after 17 cycles, you can take the sandstone and pull it apart manually because the tensile strength is so susceptible to that. And the last thing we explore in the lab quite a little bit is what happens at rock ice interfaces, because we know from bigger rock slope failures in the Alps that rock ice, if you have a bigger detachment at the Matterhorn, what you see after it is the ice that stays on the fracture behind that. So we have in the last day of the instability, we have this rock ice fracturing, This we test in this shear box, which is now a cellar here in Munich, and we use sandwich samples, where this is not a slice of ham or something, this is a slice of ice in between, and this is a Zugspitze limestone, this is a Zugspitze limestone, so we make this test. So what comes out of tests like this, you will see if you consider something like 5 meters rock overburden, you see that the stability of the sandwich sample significantly decreases from -10 to 0 degree. The same is true for 10 meters rock overburden or for 20 meters rock overburden, and roughly for 40 meters rock overburden, and then we come to the end of this physical process. And we also do such tests over longer time scales. So this is a English NERD project we've done with a German limestone, a French limestone, and an English limestone for funding reasons. And we applied these rocks for repeated freezing over 900 days to see how they evolve over longer periods of freezing cycles. They have quite a dense coverage with different instruments on them to record they record a tomographic record every 4 hours over 900 days, and also like any kind of heave or something that's on top of it. And over 900 days of repeated freeze and thaw cycles in these rocks, you can see that this previously intact rock is entirely shattered. From the top to the bottom, you see like all these cracks were induced by ice lenses that grew into it and caused like cryosuction and ice segregation pressures and destroyed the samples. You see like some of the samples had deformations in the range of 16 millimeters, which is quite a lot. But even the Wetterstein, that is a very tough limestone from the Zugspitze, had deformations in the range of 2 millimeters. Okay, if we want to take these conceptual understanding and the lack understanding of single parameters, how they change upon thawing, to the field, we have to first understand how the permafrost really evolves inside the rocks, and then secondly, what is the mechanical implication of this. This we do again at the Zugspitze. So there we have quite a good overview over the last 10 years how permafrost evolves. And we're doing this because boreholes are very particular and only record the thermal field in a very narrow section, that's 10 centimeters around the borehole. We use this electrical resistivity tomography, so a geophysical tool I've been working on. So that was my PhD basically, to develop that in rock faces. And I quickly show you the work of this. This is the frozen gallery at the Zugspitze. You see this is the outer rock face. Even in winter, we have parts of the rock face that are so steep that they do not accumulate snow. And these are the parts that really have permafrost because they can emit a lot of heat over the winter. 30 meters behind this rock face, there's a gallery. This is this gallery here. And here we're having all our electrodes in. So 30 meters behind us in the gallery, there are 140 electrodes. And from this, we make tomographies. And in the tomographies, you see this bluish part is then the part that freezes and thaws. Okay, I'll go quickly over that. We take samples to the lab, we calibrate them. We have a curve comparing rock temperature and the electrical resistivity, which we can use to calibrate these curves. And from this, we can then make tomographies to see how permafrost evolves over multiple years. Okay, let's quickly check how they look like. This is the snow-free rock face, which significantly cools in February here. And you see this is a permafrost lens with a dimension of 70 meters by 30 meters. And for the first time, basically in geophysics, we could calibrate it well enough to really write temperatures here, to not only write frozen, unfrozen, but to really write temperatures here. And if we go down to August, we see like temperatures below -2 degrees only occur 20 meters away from the rock face. In September, October, it cools again, and the part that is frozen increases again. We can do this now. We do this now basically monthly since 2014. So with this, you can see the rise and the decline of the permafrost lens. You can also see years where it's extending quite a lot. And with this, we can see the long-term performance of it. Okay, I try to show you this now in 3D as well. So we can also like cut rock crest lines like this into pieces And you see there's ice-filled fractures in here. I show you one of this. There's 10 centimeters across. And from this, we can now cut this rock crest line every 4 meters in a bit. And from 2006 to 2008, we see the bluish colors here are the frozen rock inside. And you can see that from here to here, you can see how it starts to thaw. We've done this now for basically 14 years. And in the 14 years, you can see like how the frozen parts decline more and more, and we get less and less permafrost in the ridge. And we can even use the technique to quantify the amount of cubic meters that still have permafrost. But in many of these pieces here, you can see like how it declined in there, and we can now suddenly look inside mountains and see how permafrost changes. Okay, I'll show you a practical example of that is the Iki where we applied that to a cable car. This fracture here produced significant water inflow in fractures in 2003, and it's quite a enormous touristic spot up here that has 8,000 people per day coming up, paying 60 euros. So they wanted to know, where does the water come from, this fracture? And so we did upsiling. We used tilties to drill in electrodes, and we did 3 tomographies of this. And we're now looking at one of the Piton Centrale. And the Piton Centrale has 2 artificial structures in there, which is like a French room they use for lunchtime, and it's quite heated, quite a lot, it's warm. And an Italian room on the other side, which is smaller but even hotter. So the French said it's the Italians because they heat too much, it's too warm in the room, and the Italians said the French have a much bigger room. So we made a tomography here to find out, like, where does this thermal influence come? And the big fracture that put out a lot of water runs across here. And this is the French lunchroom. This is the tomography we did. So in this, you can see blue is again the frozen. You can see like this artificial structure, the lunchroom, creates quite some heat emission into the rock, which is visible in the tomography. The fracture runs along here. This is the Italian rooms. And you can see that the heat emission from these artificial probably had an impact on the permafrost state up there. Okay, I go quickly over that. So what can we do with this kind of information now? And what can we learn out of it? So what I say is, can we develop, I call this a bilingual model that understands thermal impacts and can transfer them into mechanical models? How do we do this? So we take the samples into the lab, so I showed. We've taken a field site where we observe such a destabilization over 10 years, and then we try to develop a benchmark methodology where we can translate thermal influences into mechanical influences. So our study site is the Zugspitze. This is the Austrian Zugspitze cable car. You see, this rock slide here has already displaced quite a little bit. We see something we call an harnish, like 40 centimeters of polished rock that have already been exposed by the sliding in here. If you go deeper into this rock slide, you find permanently ice-filled fractures down here, which you see in there. And we have significant displacement. And typically for permafrost rock slope failures, these displacements accelerate by a factor of 10 in late summer. So we have 5 to 10 times faster moving rates in September in comparison to the rest of the year, except summer. From this side, and this is really the benchmark side where we developed the first mechanical model, where we can anticipate what's happening in future, though it's published something like 2 months ago. We took hundreds of samples to test how the compressive strength changes. And upon thawing, the compressive strength changes by 20 to 50%. Tensile strength changes by 15 to 70%, fracture toughness by this value, basic joint angle reduces a little bit, and the shear strength of rock ice context is also in there. Did I do that? Okay, don't know how to get this away here. Okay, the next thing we had to find out is like how much permafrost is still in there. So for this, we used now geophysical methods to see like how much is frozen. So this is the part of it that's still frozen, and then we developed a model of how much thaw we would get over the next decades. Okay, so leave it like that. I think you can still see that. So with all the information combined, we can now make a model that tells us something. How will this rock slope failure develop in future? This is 100 years ago. With frozen conditions, we still had a factor of safety that is 2.55, so a relatively stable rock slope. This is the present day, so the factor of safety is 1.25 as an average over the year. But if we take summer temperatures, we get close to a factor of safety of 1, and we see this displacement. If we continue the warming in here, just using the mechanical parameters we have from the lab, we will see that this stabilizes in future. And I think this is the first example really where in a mechanical model we can show why permafrost rocks become unstable in a warming permafrost environment. Okay, we're currently working on the point, can we generalize that? Can we apply that to the entire Himalaya or the entire Alps? What are the parameters we have to put into this? And this is one of my last slides I have for today. There are two types of variability we should take into this. We've seen different rock types react more or less sensitive. They all react, but more or less sensitive. And then we can also see that certain gradients, slope gradients, are very susceptible to these changes. And these are probably those between 55 and 70 degrees. Small changes in mechanical parameters have a big impact on the susceptibility to create rock slope failure in there. Okay, I'm showing you a little bit more practical examples now. We've also been doing this for Norway in a project where we deal with the evolution of fjords. And there's a big paradoxon, basically, a big scientific problem, which you also have in the Alps. The glacier retreat 15,000 years ago, but then it takes 6,000–7,000 years before the big rock slope failures come down. Why is that? Why do we have such response time? And in the case of Norway, we created a fjord model that is a model here that has the ice pressure. You see the arrows are the ice pressure. Then we have a physical model to see the permafrost evolution in the late glacial. And only if the permafrost gets out, we then start to get the big rock slope failures. So I'm restarting this. This is the retreating ice level in here in the late glacial. In very cold conditions, we get 300-meter deep permafrost evolving that shields it and protects it. And only in the Holocene, then 8,000 years before present, we get the big rock slope failures, because then the mechanical alteration and the retreating permafrost allows the big deformation of these rock slope failures. Okay, if we try to summarize that, what I wanted to tell you is like we're currently at a stage where we try to link the thermal evolution of permafrost in the future with the mechanical evolution to understand what can happen. And we are now approaching the ability to creating very highly calibrated discontinuum models for single cable cars, or so, to start to anticipate how the evolution will be in the next 50 years. So this is on an infrastructure scale. At the same time, we try to understand landscape evolution over longer time scales. So there we have to be much more inaccurate. We can't put single fractures or something, but we have to operate over long times. The biggest scientific problem we have at the moment is what happens with material that is exposed to frost over 10,000 years. It doesn't stay the same. And there are two ways to do it. Like the one is to say like every frost cycle creates a damage. This is called fatigue. Or to say like 10,000 years of frost create a slow progressive damage. This is called time-dependent material weakening or subcritical fracture propagation. So these are two things. We have 2 PhDs on this, and I think this is still a very difficult thing. Okay, and with that, I'm just talking about the mechanics of the detachment. I haven't talked about the mechanics that follow if these identical rock slope failure falls onto a ground that was previously frozen and is now unfrozen and much easier deformable or small material to erode. And this is something we've explored in a new article that just came out this week in Nature Communications, and it's called The Mechanics of Landslide Mobility with Erosion, where we try to investigate effects of what happens if identical rock slope failures fall onto a ground that's much easier to deform. I take you last 3 pictures to show how this works in practice. What I'm saying is the kind of things we develop in science have a very short way until we use them in practical applications on cable cars and alpine huts. And I bring you to this alpine hut here, which is the Studelhütte, is the main access to the highest mountain of Austria, the Großglockner. And we have significant deformations on the north side. So this is 2,900 meters roughly. And here we have a big permafrost related creep feature that now starts to undercut the northern part of the slope. You see we do laser scanning on this. On the laser scan, you can see easy from the surface pattern on the roughness, the big movement we get in here. And we also did like EAT profiles to see like the thermal state. With that, we can first generate deformation patterns. You see we have deformations of 50 centimeters to 70 centimeters in the 2 recorded years, just below the hut in this permafrost supported solifluction lobe. And the second thing we can do then is looking with EAT in what is the reason for this. And we see that this hut above here has created a significant warming bulb under it, which is 10 meters deep. And also close to the hut, the northern face, which should be frozen, is not frozen anymore. So the first thing we recommended them in 2017 is to put away the water from the roof that was always put into the northern lobe. And by that, we could see like simply in 1 year, we also have thermal sensors to show that, that the northern slope started to restabilize a little bit and to get cooler because it's had no water penetration coming from above. Okay, let's summarize this. Degrading permafrost causes massive changes in rock and ice mechanical properties and also cryo and hydrostatic pressures. We can use geophysical techniques to provide quantitative insights into these properties. We are presently developing mechanical models that show rock instability on a relevant infrastructure, time and spatial scale. We can also apply that to geomorphological timescales where we have to do a lot of thinking about what happens with material exposed to cold conditions over longer timescales. This is published in a number of articles here, so we have ideas and initial models, but I think it remains quite a tricky question. And with that, I want to say we need to quickly enhance our predictive understanding of alpine permafrost systems to anticipate the evolving hazard. Because in this case, this is the only kind of understanding we have. We have no history that tells us what's going to happen in the next 50 years, or we can just use this kind of understanding to see what kind of hazards we're running into this. If my talk was too superficial, there are a number of papers behind, and I'm very happy to send you some of those. But I'm also very happy to answer your question right now, and perhaps I can address it quite out. Thanks very much for your attention, and I'm looking forward to your questions.